Hi, everyone. I'm Lily. I'm a student from UC Berkeley, and I'm also part of Anyscale. So today, I'm happy to give you the talk about efficient LLM deployment, a unified approach with Ray, vLLM, and Kubernetes. So for today's talk, I will begin by discussing various infrastructure challenges associated with generative AI workloads. Then I will cover Kubernetes and KubeRay, how to leverage those two techniques to manage the clusters for those demanding applications. Then we'll talk about those Ray AI libraries, including Ray Data, training, serving, and Ray 2. And lastly, I will also introduce vLLM, an efficient inference engine for LLM serving. OK, so let's get started. I outline three major challenges in generative AI workloads nowadays. So the first one is the scale. The scale of the models is numerous, and the second is the pipeline of those LLM workloads are quite complicated. And lastly is the efficiency of those LLM serving is very low. We don't have high efficiency. So I will dive those challenges in one by one, and then tell how those techniques can be used to solve those challenges. So first, as we all know, the past few years have witnessed the rapid growth of model size, like large language models. So if you look at the timeline here, that we can see notable model size, notable models like GPT-3, Bloom, each progressively larger than its previous generations. And as we move forward in time, the model size increased dramatically, with models reaching up to hundreds of billions of parameters. And the trend is visible with examples such as Llama 3.1 and 405 billion parameters, or Grok model with over 300 billion parameters, or OpenAI GPT series. So why are the generative AI models get bigger and bigger? So the reason is that as we increase the number of parameters, those models also tend to demonstrate better accuracy. So larger models are generally more capable of understanding complex language patterns, which improve their effectiveness across a wider range of tasks. So as we can see here, small models have limited capabilities, in areas like question answering or arithmetic. However, as models grow larger, not only do their question answering arithmetic skills improve, but they also begin to demonstrate additional abilities, such as summarization and code completion. But at the same time, as the model grows larger, the compute required to train those models increase at an extraordinary rate. So in fact, as illustrated here, training compute has been growing 10 times every 18 months. But in contrast, the Moore's law shows that general-purpose CPU advancement grow at a much slower rate. So it doublings about every 18 months. So there is a gap here between the demand of the generative AI workloads and the supply we can provide by the current hardware. So as this gap grows, specialized hardware like GPUs, TPUs are developed to support those workloads. We have NVIDIA GPUs, AMD GPUs, TPUs, different hardware. Now, question is that with those advanced hardware, specialized hardware, can we solve the problem? And the answer here is it's not enough. So similar story. Even with those specialized hardware, the gap between the demand and the supply increases 256 times every 18 months. So that being said, a single machine or a single hardware is definitely not enough to train those large language models. Actually, nowadays, as model grows larger and larger, a single node may not even be enough for serving the model. So let's talk about the scalability requirements for the current generative AI workloads today. So with a single node, a single machine, maybe you have multiple GPUs on a single machine, you can fine-tune a small model locally on limited data set. This is feasible for for small tasks, but quickly become insufficient as models and data grow. To fine-tune a middle-scale model, you need a larger setup from 1 to 100 nodes. This allows you to distribute the model across multiple machines and leverage data parallelism to process larger data set efficiently. Batch inference is also possible on larger scale, unstructured data at this level. However, if you want to train a foundation model from scratch, like a model with billions of parameters trained on trillions of tokens, you need 100 or even thousands of nodes. So this is the scale at which major AI companies operate on to develop state-of-the-art models. That being said, with such large scalability of current generative AI workloads, you really need an AI infrastructure that can manage, observe such a large amount of data and compute resources. And the second challenge in generative AI workloads nowadays is the complexity. So let me give you a very concrete example, RLHF. So what is RLHF? It's reinforcement learning with human feedback. So it is a technique nowadays people use to improve the quality, like make the model safer, like has a better quality, generate a better answers. So like GPT models, most of the models nowadays we use, they are trained with RLHF. So what is RLHF really doing here? Let's look at those pipelines in more detail. So the first step of RLHF is you need to do some like fine tuning. So basically you will have some input data and you send to some labeler. You hire some labeler. You pay them the money to let them generate the correct answer, like the good answer for those prompts. And then you fine tune the model on those data. The second step is, so the first step is just to make the model generate some reasonable output. So instead of repeating the question. The second step is you will use human feedback to improve the model. You will still hire some labelers, and you will give the labeler some like example answers, and you will let the labelers to decide which answer is better. And you use those information to train a reward model. So what is a reward model? A reward model is saying that, oh, given the prompt, the model generates two answers, answer A and answer B. Which answer is better, right? So the reward model will tell us, oh, answer A is better than answer B. So this is like a judgment, right? So this is a reward model. And the last step, you train a policy model. So what is a policy model? So in the ideal case, you want the large language model to generate a good answer automatically. So what you will do is you will let the LLM to generate some answers, and you will reward the model to score those answers. And you will give higher score to those good answers, give low score to those bad answers. And you will use those information to update the LLM model parameters so that the LLM can learn that, oh, I should always generate a good answer instead of saying some instead of generating some bad outputs. So those are the three steps of RLHF, and I think this is very important for nowadays for LLM to have a good performance. But if you look at this pipeline, it's quite complex. So you have like some data cleaning, data labeling, right? So you need to prepare the data for the labeler. You also have some model inference, right? Because you ask the model to generate some answer first, and then ask a labeler to score which answer is bad, which answer is good, which answer is bad. You also need to sample some output to train the policy model. So you need to do the model inference. And also you need to do model training, and you need to train 3 models, right? So first, you need to fine-tune the model to make the model generate some reasonable output. Second, you need to train the reward model. So basically, you need to know which answer is good, which answer is bad. So you need to train the reward model. And lastly, you need to train the policy model to update the large language model to make it generate the final output. So you need to train 3 models. As you can see here that a single RLHF pipeline, it involves data processing, model inference, model serving, and model training. So what this means, it means that we kind of need we need a layered infrastructure so that those AI scientists, machine learning scientists, they can focus on like data processing, model training, or model inference. And other people, like infrastructure engineer, they can handle those infrastructure stuff, like how to handle the machines, how to handle the clusters. Basically, we want to separate the tasks because this pipeline is quite complicated. And the last challenge I want to mention today is about the LLM serving efficiency. So serving large language models is surprisingly slow and expensive. Before vLLM, let me give you a concrete example. A single A100 GPU, which is kind of advanced GPU, can serve only less than 1 request per second for a moderate size of model, like 13 billion parameter model. It's a moderate size. It's not a very big. Yeah. But even with a moderate size model, you can only serve less than 1 request per second, which it means like if you have hundreds of users or thousands of users, you need tons of GPUs to achieve a good performance. And we can see like questions like how do we serve LLM more efficiently? So looking back on those challenges, so what are the possible solutions? So I will dive into 3 directions to solve the challenges. The first one is Kubernetes plus KubeArray. The second is Ray Data, Ray Train, Ray Serve, Ray 2, which are those like Ray AI libraries to facilitate the users to develop AI applications. And lastly, I will introduce vLLM. So let's dive into Kubernetes plus KubeArray. So this is an overview of how Ray integrates with Kubernetes to create a scalable and flexible infrastructure for AI workloads. On the top level are different Ray AI library. Right? You have Ray Data for manage large-scale data. You have Ray Train to do distributed model training. Like you have Ray 2 to do hyperparameter tuning, Ray Serve to do model serving. And below the Ray AI libraries, you have the Ray core. So the Ray core layers, they include some like core functionalities and integrations that can power the distributed infrastructure. So this layer ensures that Ray can work across various environments from on-premise clusters to cloud-based solutions. And lastly, you have the KubeArray. So KubeArray is highlighted in these slides as a critical technique. It's a critical integration point between Ray and Kubernetes. So KubeArray manages the lifecycle of Ray clusters and their applications within Kubernetes environments. It enables Ray workloads to be orchestrated on Kubernetes. And the last layer and the bottom is a Kubernetes and cloud VMs. So Kubernetes provides a container orchestration layer, which manages the deployment, scaling, and operation of Ray clusters. And cloud VMs allow the infrastructure to be scaled on demand, ensuring that the resource can match the workload requirements. So what's the benefit of such a layered structure? So this layered structure with KubeArray provides a clear separation between the separation of the responsibilities between the data ML scientists and the infrastructure engineers. So the data and ML scientists, they only write some Python scripts within the Ray environment to create different tasks to check the health, to handle like those scaling requests for distributed AI workloads. And for those infrastructure engineers, they manage the Kubernetes environment. They integrate KubeArray with Kubernetes ecosystems, can use different tools we have in Kubernetes. So why do we want to use Ray on Kubernetes? I think the answer is kind of obvious. So we want to leverage those benefits of Kubernetes, right? Like it has some infrastructure automations. Kubernetes automates the deployment, scaling of those containerized applications, reduce the manual effort required to set up and maintain those infrastructure. And also the scalability. So Kubernetes has good design for horizontal scalability, making it ideal to scale those Ray clusters. And also like high availability, reliability, resource efficiency, and multi-cloud deployment. So all those benefits make us want to leverage it, use the Kubernetes with the ring. So next, let's shift our focus to like ray data, ray train, and ray serve, those ray libraries, to enable the users to build AI applications without the need to manage underlying infrastructure. So the first is ray data. So what is ray data? So you can think of ray data as a last mile bridge. It connects the storage or the ETL pipeline outputs to the distributed applications within the ray ecosystem. So it enables the users to load and pre-process data for distributed machine learning training pipelines. And it offers some key features. For example, it can provide fast recovery from like out-of-memory error. It can support for heterogeneous clusters, and it can it can guarantee data integrity, right? So it will not have any dropped rows during the distributed dataset iteration. So after you get the data from the ray data, you will go to ray train, right? So what is ray train? So ray train is just an easier way, like for users to focus solely on the training logic without having to manage the infrastructure. To be more concrete, so what the user need to do? So user need to first specify the desired setting, right? Like how many GPUs, how many CPUs to use, what are the resources I need? And the second, what is the training function, right? So they can use PyTorch, TensorFlow, and all other deep learning framework to write their own training logic, right? Customized training logic. And next, the ray train will distribute the training process across multiple nodes without requiring the users to manually handle the details of like resource allocation, fault tolerance, or parallel processing. So after you train the model, you want to do the serving. So when you want to do the serving, you will do ring serve. So what is ring serve? Ring serve is a serving library. So it can handle multiple it can provide the infrastructure to deploy and manage ML models in production. So more specifically, it provides some important features. For example, it can do multi-server model deployment. So this is very important for large models, right? Like if the model is like hundreds of billions parameters, sometimes it will scale multiple nodes to serve a single model. So you want to do multi-server model deployment. And also if the request rate is very high, you want to replicate the nodes. So in that case, you might also want to have multiple servers to serve the same model. And second, it can do auto-scaling. So RayServe automatically adjusts the number of instances based on the traffic. It will scaling up during the high demand and scaling down during the low demand. It also do load balancing, right? So it will evenly distribute the requests across available servers, maximizing performance. And lastly, it can do failure recovery. It includes some built-in failure recovery mechanism to ensure the model availability and resilience. And below the RayServe is a vLLM. So RayServe only handle multi-server deployment, auto-scaling, load balancing, failure recovery. But when you actually run the transformer models, you will use the inference engine, vLLM, which is also developed from UC Berkeley, and I will dive into later. Okay, so let's dive into vLLM. So what is vLLM? So vLLM is a fast and easy to use open source LLM inference and serving engine. So it is a serving engine used by RayServe and actually many other companies. So we launched the project, the vLLM project, in June 2023, when there were only few open source projects for LLM serving. And fortunately, vLLM got a lot of attraction from the beginning and has become one of the most popular projects in this field. We also get many users across industry, including major cloud providers like AWS and Google Cloud. So why is vLLM fast? So today I will only point out 2 features, but there are actually a list of features that can enable the fast serving of vLLM. So one of the most important feature of vLLM is continuous batching. So what is continuous batching? So when you do model inference, when you do like LLM text generation, it's actually very hard to fully utilize the GPU. Why is the case? Because when you generate the answer for a given prompt, you don't know the output length, right? Like for example, given the prompt, like what is your name? The answer can be my name is Lily, or my name is a very long word, or the model might have some chat, oh, thanks for asking the question, my name is blah, 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 blah. So you don't know the model output length in advance. So in that case, how do you do the memory management? So especially when you do the batching, when you batch different prompts in the same batch, and all of them might have different generation lengths, how to batch them together? So the left picture is an example of static batch. So basically, you will assume that each request have a fixed generation length. They will all generate 200 tokens, and you pre-allocate memory for those 200 tokens. But the problem is that in that case, you are wasting a lot of memory. You don't put enough requests in the same batch, and the GPU is underutilized. And what is continuous batching? So continuous batching is saying that I understand that we don't know the output length of the request, but let's still put them in the same batch, and we have some mechanism to separate them out when we finish the generation. So in that case, you can squeeze different requests in the same batch and make sure that all the requests can be run in a single forward pass so that you can increase the GPU utilization. So that is continuous batching. So basically, batch requests of different lengths into the same batch to increase your batch size, to reduce the waste of the memory. And the second reason is vLLM utilize efficient kernel and memory management for attention operators. So we call it page attention. And it can manage the KV cache like operating system virtual memory. So instead of allocating the memory for the whole request, it manages the memory like block by block. So we have the idea of block, so basically the memory for each token. So it's a little bit complicated, so I encourage you to check out the page attention paper for details. And also the second question is, why do people choose vLLM? The reason is that the API is pretty easy to use. So if you have a GPU, like you can just try this, like pip install vLLM, and you use the 4 lines here to try to run the like large language model. Don't use like Llama 3 8B, it's too big. Try a small model, and maybe you can run it. And also, vLLMs have some other important features to make it widely adopted. So the first one has broad model support. So like it's an official launch partner of Llama, right? Like support like Llama 400B, 70B, 8B, and it also we also accept contribution from those state-of-art vision language models training companies like Pictorial or QNVL. And the last features I just mentioned today is for vLLM, it has multi-hardware support. So because vLLM depends on PyTorch, and instead of relying on some external compilers or formats like Onyx, vLLM directly use PyTorch as a narrow waist, a middle ground to connect different backends with hardware-agnostic models and utilities. Okay, so with vLLM, Reserve, Kubernetes, how will the end-to-end LLM serving architecture look like? So first, you will use vLLM as an inference engine. And second, you will use Reserve, and Reserve will call the vLLM, right? Like it will, but Reserve will handle the model deployment, scaling, request routing, load balancing, and fault tolerance. And on top of that, you will use Kubernetes to bridge the gap between the Reserve and the Kubernetes. And lastly, you will just use Kubernetes to do the container orchestration. So those 4 layers together form a pipeline, end-to-end architecture for the LLM serving. Okay, so in conclusion, so today I talk about the different challenges we have in generative AI workloads. And I mentioned the scalable infrastructure with Kubernetes and KubeArray. And also I introduced different array AI libraries to improve the development efficiency of end users. And lastly, I introduced vLLM. That's the end of this talk, and I'm happy to take questions. Yeah, thank you.
With vLLMs, when you're batching, I'm pretty old, but do the new A100s have some form of memory protection? Because when you're doing multi-tenancy on GPU memory, there's no memory protection inside. There's no TLB. There's nothing to protect your memory.
Okay, thanks for the question. So no, the short answer is no. So currently, for vLLM, we don't do multi-tenancy. So basically, a single GPU only hosts a single model.
Well, if you have multiple prompts coming in from different locations, even though it's a single model, that's the question I was having. So you're serving, you have multiple users coming in with different prompts coming in, and you're batching across those different prompts. Then
they will be put in the same batch, but yeah.
Is that the reason why sometimes you can get random responses from other people?
Not really. Like if the inference engine is implemented correctly, it should not get the answer from other user. But the output from the other user might affect the numerical stability of the current user. They will affect each other a little bit, but you should not get the answer from the other user. Yeah.